Start recording. And so I think those are the main things about Landscape Live. And without delay, I would like to introduce today's speaker and welcome him. It is Dr. Dongfeng Li. Dongfeng is, he did his PhD at the National University of Singapore and is currently an assistant professor at Peking University. And today he will be talking about the implications of modern climate change on landscape processes and sediment flux in the high mountains of Asia. So Dongfeng, you can take the lead.
Thank you, Aditi, for the introduction. And hello, everyone. Good morning, good afternoon, and good evening to our friends and colleagues. So thank you for the invitation, and thank you all for joining. It's really my great honor to share some of my research with you to take this chance. So today I will present the research about the modern climate change-driven landscape processes in cryospheric basins, and most of the study area is based on in the high mountain Asia, where I did most of my work there. So, well, before the beginning of my talk, I would like to acknowledge my collaborators worldwide to thank their contribution to the talk to the research works that I'm going to talk later. Well, in today's talk, I will cover 4 topics, and in the very beginning, I will introduce the amplified climate change and the cryosphere degradation in high mountain Asia, and then discuss how such a changing climate and the cryosphere they can affect the slope instability, extreme floods, and also erosion and sediment flux. And in the last, I hope to I will discuss how the changing landscapes and the sediment flux they can affect the water quality, carbon dynamics, and also for the mountain infrastructure, especially for the hydropower systems. Well, this is from the latest IPCC report, and it clearly demonstrates that the modern climate change since the 1950 has changed our Earth system substantially, with the clear and robust evidence from the glacier melt, wildfires, floods, and drought. But the geomorphic impact of the modern climate change remain less studied. For example, from this is a commentary paper led by M. East. It summarizes the challenges and also the opportunities to measure and attribute the geomorphic response to modern climate change. So there are many challenges to attribute the geomorphic response to modern climate change, for example, due to the lack of the long-term and high-resolution observed data, and also because of the noise signal. For example, the land use change, they can disturb the sedimentary signal. But there are also opportunities, and one of them is to select the very sensitive study sites. For example, in the cold regions, because of the existence of the glacier and permafrost, such icy landscapes, they are very responsive, very sensitive to the climate change. So my study area mostly focusing on the high mountain Asia, as you can see from this map, that it is basically it includes the Tibetan Plateau here, and also including the surrounding high Asian mountains such as the Himalaya in the south, the Hindu Kush in the west, and Karakoram here, and also the Tian Shan in the north. So it's really it is called the Earth's third pole region, because it has the third largest glacier and permafrost systems just after the 2 polar regions. So it is also the Asian water tower. So all these large Asian rivers like the Yellow River, Yangtze River, Mekong, Ganges, Brahmaputra River, Indus River, they originate from the high mountain Asia. And such a large Asian river systems, they transport water, sediment, nutrients, and also provide ecosystem services to many millions of people in the downstream. So these large Asian rivers are super important too. And actually, for such large Asian rivers, they are also very important sediment sources from a global perspective. For example, our study, we estimate such high mountain Asia rivers, they annually transport around 2 gigaton suspended sediment flux to the downstream. And this this number is twice that than that the suspended sediment flux from the Greenland, and 5 times than that from the Pan-Arctic rivers. So we can say that the high mountain Asia rivers, they are also very important. They are also very important sediment sources from a global perspective. So the climate here in high mountain Asia is becoming warmer and wetter over the past decades. So if we look at the left figure from here, we can see that the red is the temperature change trends for the Arctic, and the blue is the third pole. So similar to the Arctic, the temperature in the third pole or the high mountain Asia is rising faster, much faster than the global average, the black line here. And here we collect climate data, temperature and precipitation data from over 100 meteorological stations, and found that the temperature increase rate at the third pole is roughly 0.32 degrees Celsius per decade. And the precipitation also overall increased after the middle 1990s, after the end of 1995. So we can say that after the middle 1990s, the climate here is becoming warmer and wetter, and such a changing climate, they can affect the physical landscapes in the high mountain Asia substantially. So in response to such amplified climate change, the glaciers, as I have mentioned, there are huge amounts, large volumes of glaciers here in high mountain Asia, and you can see from these pictures to see how the rapid change of these glacial landscapes from the 1956 to the 2007, to see the retreat and also the thinning of the glaciers and the expansion of the proglacial lakes. And if we look at this left map, we can see this map is denotes the change of the glacier mass balance. So the red dots means the negative glacier mass balance, and especially we can see in the southeastern Tibetan Plateau here, the glaciers is retreating and thinning very fast, and here the mean elevation change rate is like 1 meter per year. So if we think the glacier is 10 meters thick, after 10 years, this glacier can disappear. And in addition to the glaciers, permafrost is also very important in the third pole, and so permafrost is the frozen ground beneath our feet. So and with the temperature increase, or the permafrost temperature is also increasing. So the left figure shows that the permafrost, the ground temperature change trends from the 1950 to 26 in the northern hemisphere, including the third pole. And the red bottom figure shows that with temperature increase, the permafrost active layer is also becoming thickening, or the permafrost active layer thickness is also increasing, and because also of there are large amounts of ground ice stored in the permafrost systems, and the melt of the ground ice, they can destabilize the landscapes and cause the increase of the source lumps or the abrupt erosion features. And as you can see from this insert map, and this will affect the sediment, provide additional sediment supply into the river systems, and I will discuss more here around this aspect later. So in our study, we also introduce a concept called the mountain irritable landscape. It is defined as the most relevant landscapes, including the active glaciers, permafrost slopes, and fluvial channels that contribute to runoff and sediment processes in cold mountainous environment. So from this diagram, we can see the red shaded area. It is defined as the mountain irritable landscape, or we can use the ACDA, this proxy, the active contributing drainage area, to calculate the area of the irritable landscape. So basically, we think that for a given month in a year, for example, in May, we think this red shaded area with temperature above 0 degree, we think degrees Celsius. So we think this red shaded area is the active contributing drainage area. They can actively contribute runoff and water and sediment to the basin downstream. And in response to the temperature increase, the ACDA has also been increasing substantially from the 1960 to the present day. And this will have an important implication for the basin-wide water and sediment flux. So far we know that the climate change here in high mountain Asia is very fast, and the glaciers has been retreating, and permafrost is thawing. And this will have important implication for the stability of the landscapes. For example, for the slope instability, and in some cases they can trigger outburst flood. So here in this middle map, we can see for the yellow dots, they represent the cryospheric hazards. Here there are 12 cryospheric hazards after the 2000 cases that have been recorded in the high mountain Asia, and including the rock ice avalanche, also including the glacial lake outburst flood or the landslide lake outburst flood. All of them occur close or within the glacier and the permafrost systems. And now I will show a few examples to illustrate how the climate change and the cryosphere degradation, they can potentially be linked to such extreme hazard. So the first case is the 2021 Chamoli rock ice avalanche event. So in 2021, in the Indian Himalaya, a huge chunk of ice and rock collapsed from this Rotini peak, and the volume of the rock and ice was estimated to be 27 million cubic meters. So a huge chunk of ice and rock collapsed over 2,000 meters and fall into this progressive valley. And the melt of the ice and further trigger the debris flow that destroyed two hydropower projects in the downstream, and also caused the deaths of 200 people. So this disaster is not too far away from us, and just occurred in 2021. Another case is glacier lake outburst flood, the Gomba Tongsha glacier lake outburst flood. It is also a transboundary disaster. So here, if you look at the red top corner, here is the glacier lake, and it is actually a very small glacier lake. And if you look at the picture here, the volume is like 0.1 million cubic meter water, but this small glacier lake outburst has triggered a big disaster. And so in 2016, a heavy rainfall event triggered debris flow that flushed into this glacier lake and caused the breach of the glacier lake, and further caused the. So here is the boundary between the upstream China and the downstream Nepal, and so the glacier lake was located in the Tibet of China, but it has when the Gulf occurred, or glacier lake outburst flood occurred, it have the downstream impacts for the downstream country Nepal, and destroyed this hydropower project has also caused substantial riverbank erosion, and this threatened many houses and infrastructure along the river valley. And now I will show two examples in the southeastern Tibetan plateau, because as I mentioned before, the glacier in the southeastern Tibetan is retreating especially very fast. And here is a case of the Jingwu glacier lake outburst flood in 2020. So in the June of 2020, also a heavy rainfall event triggered a landslide. This landslide occurred in a lateral marine zone. So this landslide fall into this glacier lake and caused the displacement wave that further caused the breach of the glacier lake, and generated this big flood event for the downstream. And another case, this is also a glacier lake outburst flood, and another case also occurred in the same tributary river, in the Yigung River, is the landslide lake outburst flood. This disaster was a bit earlier in 2000. So a landslide from the progressive area dammed the Yigung River and formed this Yigung Lake. this landslide dammed the river for 2 months. So after the breaching of the lake, it caused a super high magnitude flood, and the peak discharge of the outburst flood was estimated to be 120 cubic meter per second. So it is one of the largest flood event recorded in the region over the past century. So if we summarize such processes, we can see, so climate change has caused the deglaciation, and the newly exposed landscapes, the periglacial landscapes, they are unstable and prone to landslides and debris flow and rockfalls, and triggered the outburst flood. So also with climate change, there could be more extreme rainfall that could further amplify or exacerbate such processes, and also exacerbate such a flood. And they can trigger both glacier lake outburst flood or the landslide lake outburst flood. So the next question we hope to address is to address how does the modern climate change and also the cryosphere degradation, as well as the changing hill slopes processes, they can affect the fluvial sediment supply and fluxes in the region. So to answer this question, we focus on the quasi-pristine headwater river systems without human activities like dams or land use change. So here we collect the historical data, historical runoff and sediment flux data in the high mountain Asia from 1950 to 2010. So in total we collect the data from 28 headwater river systems across the high mountain Asia, but we do not have much data in the Himalaya. So overall, we found that both the annual runoff and also the annual suspended sediment flux have substantially increased over the past 6 decades, and for the river runoff, on average, it increased at a rate of 5% per decade, but for sediment load, it increased at a rate of 13% per decade. And especially, we found that in the western part of the region, for such headwater river systems in the upper Indus River and also the upstream river, their annual runoff and sediment loads increase much faster as compared with this monsoon-controlled eastern basins. This is mainly because in the western part there are more glaciers here, and such river systems they are responding more faster to the climate change. Well, from this figure, we can see more clearly the time series of the river runoff and the sediment load. If we look at figure D is for the river runoff and figure E is for the sediment load, we can see the slight increase from the 1960 to the 2017, but after 1995, the increase actually accelerated for both runoff and sediment load. And such acceleration in runoff and sediment load, they are in line with the faster increases in air temperature and also precipitation, and also be consistent with the changes of the glaciers and permafrost. So we also read a review paper to summarize the processes to illustrate how the warming temperature they can affect the glacial dynamics and also affect the sediment availability and also the transport capacity, and finally result in the increase of sediment load in the glacier systems. So one process is because of the periglacial process as introduced by Professor Michael Church. I also see Mike is here, and so also take this opportunity to acknowledge his contribution. So with glacier retreat, the newly exposed periglacial landscapes, they are unstable. They can provide new sediment supply into the river systems. And another aspect is because of the subglacial drainage networks. So with more glacial meltwater, the subglacial drainage networks, they are expanding. They can transport or export the previously accumulated sediment into the downstream river networks to enhance the basin-wide sediment export from the glacial basin. So in addition to the glaciers, the permafrost is also important, as I have mentioned. So actually, around 50% of the landscapes in high mountain Asia is underlain by permafrost. So here we also summarize how the temperature increase they can cause the ground ice melt and destabilize the permafrost landscapes through 4 types of abrupt erosion features, including the active layer detachment here, and also the thermal erosion gully, as well as the retrogressive source lumps. Especially for such retrogressive source lumps, slumps, they can channel connected source lumps, they can provide important sediment supplies from the hill slopes into the river systems. We also use a simple sediment climate elasticity model to estimate the sensitivity of sediment load to the changes in precipitation and temperature. So basically, for the high mountain Asia, our results show that we show that for every 10% increase in precipitation, it can result in a 24% increase in the sediment flux. But and for temperature, for every 1 degree increase in air temperature, it can result in a 32% increase in the sediment flux. And interestingly, for the response of sediment flux to temperature, we found that for the river basins where there are more glaciers, their sensitivity to the temperature is higher. In other words, for a river basin with larger fraction of glacial cover, they are responding more sensitive to the temperature increase. And with the sensitivity result and also together with the future climate change scenario, we predict the future change trends of the sediment flux in the region. So first, we estimate that the present day sediment flux in the high mountain Asia is 2 gigaton per year, and in a 1.5 degree warming scenario, the sediment flux will increase to over 3 gigaton per year by 2050, and under a 3 degree warming scenario plus precipitation increase by 30%. So the sediment flux will more than double and reach over 5 gigaton per year. So this is really a large increase, potential increase in within this century. So after our results from the high mountain Asia, we found the increasing sediment flux signal from the headwater river systems in the high mountain Asia. Then we want to ask whether, from a global perspective, whether we can identify the similar signals from other cold regions. So we also did a review work to synthesize the data from the European Alps, from the Andes, high mountain Asia, Arctic, as well as Greenland. So in total, we found that there are 76 rivers where there are the observation of sediment load, including both suspended sediment load and also sped load. They have such increase where in such river systems they have shown the increased sediment load signal in response to the accelerating glacial melt or the permafrost degradation. And also for the Arctic coast, there are also 18 permafrost coast sites along the Arctic that have shown the increasing coastal erosion. For example, in a few sites, the erosion in the coastal erosion rate in the 1950s like 6 meters per year, but in the 2010, the erosion rate can reach over 10 meters per year. So you can also see with the coastal permafrost degradation, and also because of the sea ice change, they can accelerate the Arctic coastal erosion. That has an important implication for the infrastructure, for example, for the oil pipelines along the Arctic coast. So after we found that the increasing signal driven by the global warming and as well as the changes in precipitation, as well as the glacier and permafrost changes, the next question we hope to ask ask the underlying processes. So for example, in this figure, we try to explain how from the process perspective, process perspective, how the temperature and the precipitation they can control the suspended sediment concentration, or short for SSC. So from this figure, in the bottom figure here, there are 5 sediment pause events. 1, 2, 3, 4, 5. So if we look at the number 2 and number 5 events, they are typical rainstorm-driven SSC events, because during these 2 events, the precipitation exceed 15 millimeters per day. But for the number 3 and number 4 events, if we look at the red is SSC, they are also very high, but exceed the 2 kilogram per cubic meter, but during these 2 events, the precipitation is very low, close to zero. But there are 2 high temperature windows, so we expect that the high temperature has caused the glacial or permafrost processes that result in the increases in the basin outlet suspended sediment concentration. So the point here is that in addition to the control for precipitation or rainfall, temperature and the thermal related processes is also important in the cold environment. So this figure is the monthly hysteresis between the SSC and discharge. So the y-axis is SSC, the x-axis is the discharge. So we can see that it is a clockwise relationship. But if we compare the SSC in September and June, we can see that the discharge in September is higher than that in the June, but the SSC in September is lower than that in the June. So what is the reason? And we explain this this phenomenon by using the change of permafrost active layer as well as the runoff generation processes. So for example, from May to September, with the increase of the air temperature and as well as the ground temperature, the active layer, the permafrost active layer, their thickness will increase. So in June, when the active layer is very thin and most of the runoff generation process is through the surface runoff. So surface runoff, they cause very severe surface erosion and result in a relatively higher SSC. But in September, when the active layer reaches thickness is maximum, the infiltration is large, and the surface runoff is relatively low. During this September, most of the runoff generation processes is dominated by the permafrost groundwater. So that's why in September, even though the discharge is relatively high, but the SSC is much lower because of the less surface erosive water. And here is a figure to show the seasonal regime shift in the sediment transport. So here we identify 4 cryosphere feed rivers, including the glacial basin, the naval basin, and also the fluvial basin, and as well as a mixed regime basin. So here I will show the regime shift, the seasonal regime shift in sediment transport from the glacial basin as well as from the naval basin. So for the glacial basin, we can see the black line here is the SSC data from the 1960, and the yellow is the data from 1980s, and the red is the data from the 2000. So we can see the substantial increases in the summer SSC for this glacial basin, mainly because of the increase of the meltwater, glacial meltwater, as well as the discharge variability or the runoff variability, because sediment transport, they are positively, there is a very positive correlation between the SSC and the runoff surge that can, when there are more runoff variability, they can enhance the sediment export for the glacial basin. For the naval basin, we can see that during the 1980s, there's only one peak, mostly driven by the snowmelt processes in April. But in the 2000, we can see there are two peaks, right? Two peaks for the SSC, and one is in the spring, also in April, but in August, we can see another sediment pause event, mainly because of the enhanced rainstorm events. So we can see such a seasonal regime shift in the sediment transport because of the changing temperature, as well as the changing glacier and snow processes, as well as the especially for the increases in rainstorm events in the summer. And we also develop a sediment availability and transport capacity model, that is short for SAT model, to simulate the SSC dynamics in cross-feed rivers. So here is our model framework. It is I think the advantage is that we not only consider the sediment transport capacity Q, but also we consider the sediment availability, especially for the thermally related sediment availability. So here's the empirical function of our model that includes the factor of temperature, and also you can see it is an exponential relationship between SSC and discharge. We also include the runoff surge factor in our model because it shows a better correlation with SSC as compared to the simply use discharge. And we also updated the model into our SAT monthly model to see, hopefully it can provide a universal framework to simulate the sediment transport processes in cross-feed, different types of cross-feed feed rivers, like the glacial basin, naval basin, or the fluvial basin. So here's the performance of our SAT model. Basically, it outperforms the conventional static sediment rating curve method by 20% in terms of the improvement of the NSE, or the Nash coefficient. And our model can also reproduce the event scale SSC event. For example, here the black line here is the observed this sediment and discharge event. The hysteresis curve, you can see it is a clockwise hysteresis, and the gray line here is the predicted sediment SSC by the traditional rating curve method. And our SAT model is the orange line. You can see we can simulate the higher SSC events, and also can simulate such lower SSC events. So we can reproduce such a hysteresis because our model considers the sediment availability in addition to the traditional transport capacity. So our model can also reproduce the decadal sediment hysteresis and regime shift, for example, to simulate for this glacial basin. We can simulate the substantial increases in the summer SSC after the 2000. Well, in the last few minutes, I will discuss the impacts of the changing sediment flux and the changing sediment transport regime for the water quality, carbon, and hydropower systems in the high mountain Asia. So because our data are mainly focusing on the suspended fan sediment in the glacier and permafrost systems, and we know that the fan sediment are easily bonded with phosphorus and most heavy metals like mercury, arsenic, and lead. Especially for such permafrost systems, they have stored a huge amounts of mercury. And in a warming climate with the permafrost collapse and the abrupt erosion, a lot of mercury, especially the particulate mercury, they can be flushed into the river systems together with the suspended sediment. So here is this picture is provided by a journalist working in the Tibet, in the Qinghai province. So the story behind this picture is that before the collapse of the permafrost, it's a small stream, and local community they can collect water from this small stream. And but after the permafrost collapse, you can see that this river was totally disturbed, and the local community they have to go to another place to find the new water source. And the increase in suspended sediment as well as the increase in turbidity, they can also affect the aquatic ecosystems, for example, to affect the spawning site of the fish, especially the fan sediment. They can cover the gravels and to cover the spawning sites of some fish. Yeah. And we know that the permafrost also is permafrost system also stores a huge amount of carbon, especially the old carbon. And there was a study that estimates that around half of the global soil carbon is stored in the permafrost system. So many of them are Holocene scale carbon, and but with abrupt permafrost collapse, for example, with the retrogressive source lumps, they can cause the erosion of the sediment and also carbon together from the hill slopes into the river systems, or from the terrestrial landscapes into the aquatic landscapes, and may also during this process, because the carbon are mobilized, they can be more easily to experience the mineralization or cause and the degradation of the carbon can cause the release of the carbon into the atmosphere. So but our study, we mainly focus on the particulate carbon because we only have the suspended sediment data. So when we estimate the future sediment flux, we can also estimate the particulate carbon. So in our study, we estimate for the river particulate carbon, including both POC and PSA, by the middle of this century, under the extreme climate change scenario, that is temperature increase by 3 degrees and precipitation also increased by 30%. The particulate carbon in the high mountain Asia rivers, they can transport 50 to 150 million tons per year. And for the hydropower systems, so here's a paper. I'm also one of the co-authors. We estimate that the global unused 2/3 of the global unused profitable hydropower is distributed across the Himalaya. So in other words, these Himalaya countries, they have the world's largest undeveloped and profitable hydropower. But because of the increasing suspended sediment load from the headwater systems in these high mountain Asia, they can potentially or negatively affect these hydropower systems. So here we take an example of take the Upper Yangtze River as an example. So we estimate the sediment trapping efficiency of this these dams is roughly over 80%. 80%. So which means that 80% of the sediment supply from the upstream, they can be trapped behind these cascade dams. And using the Upper Yangtze River as an example, we estimate that under the extreme climate change scenario, in the next 3 decades, there will be 2 gigaton suspended sediment be deposited within the cascade reservoirs. So this is also a large number that is equivalent to one of the designed storage capacity of this Liyuan reservoir in the Upper Yangtze River. And we only consider the suspended sediment if we also assume that the bed load is has been increasing. This would be very destructive to such reservoirs and affect the storage capacity and also thus the hydropower generation efficiency. So in addition to the reservoir sedimentation issue, as I have mentioned earlier, there are some extreme sediment events. For example, the debris flows, the landslides, as well as the outburst flood. They can directly destroy such hydropower systems in the Himalaya, as evidenced from the 2021 Chamoli event, as well as the Gongma Dongsha Glacier Lake outburst flood event. As well as because of the increasing sediment, they can also abrade the hydropower turbine and cost and degrade the hydropower generation efficiency. And in the future, we really need the climate change resilient hydropower systems. And one point is that we need to be forward-looking to consider the potential impact of the future climate change. Another point is that for many existing hydropower dams in the Himalaya, they didn't consider the impact of the future climate change. So for such hydropower systems, the hydropower projects, they also need to do the reevaluation to assess their whether they are suitable for the future climate change. And also we think that hydropower may not be that sustainable in the Himalaya, and because of the climate change impacts. And in addition to hydropower, we also need the other renewable energy sources to include the wind and the solar panels. Well, here is the summary of my talk. So we found that the climate change and the cryospheric degradation are destabilizing the icy mountain landscapes and also increasing the cascading hazards in high mountain Asia. Erosion and sediment fluxes have substantially increased with accelerations after the middle 1990s. And in a warm and wet future, sediment fluxes in high mountain Asia will likely more than double by the middle of this 21st century. And the changing landscapes and increasing sediment fluxes have important implications for the region's infrastructure, energy, and environmental security. For example, for the hydropower systems, as well as for the water quality and carbon dynamics. And in the future, we really need the forward-looking design and maintenance measures and sustainable sediment management solutions that can help transition towards the climate change resilient hydropower systems. And here are the publications of this talk. And we are sorry that some of the publications are not open access due to the limited funding support. But if you are interested in, please feel free to email me, and I would be more than happy to share them with you. And also, if you have any questions, I would be happy to discuss. Okay, I think I will stop here, and again, to take this opportunity to thank my collaborators. Thank you again. Yeah.
Thank you, Dongfeng. That was a really interesting talk. And we are now open for questions. And I can see that there is already a question in the chat, so I will read this one out. There's a question by Hugh, and it says that, is there any reason to suspect the proportion of suspended load to coarse bed load may change as the higher elevation systems increase in their contribution to the total yield from high mountain systems? This is clearly an important question for hydropower development, where they tend to assume a simple proportion such as 35%.
Thank you, Hugh, for this great question about the coarse bed load transport. Yes, I think the problem here is that first, this is an important question, and especially for the hydropower systems, actually compared with suspended sediment, the bed load could be more destructive because such coarse sediment, they are more difficult to be flushed out. And but the problem here in the Himalaya is that there are very little observation for the bed load, or there are very few observations, especially for the Himalaya scale study. I think there are in some local rivers or over a short event, for example, in Christine Cook's study, they use the seismic signal to measure the bed load transport. But this is only for an event scale, and we do not know the proportion of the bed load to the total load. And from my understanding, I would because we see such a substantial increase in signal in the suspended sediment load, and I would expect to see a similar increase for the bed load, but the increase rate as well as their spatial variation, I mean from the upstream to downstream, and also from the highly glaciarized basins to other permafrost basins, such increase rate could be different. And it also depends on the connectivity between the different river systems. Yeah.
Thank you, Dongfeng. I think that answers Hugh's question. So I'll let Luca take the next question.
And Hugh Sinclair just says, thanks to you, Dongfeng. So we have a short question from Daisy Huang, who is basically looking at the larger system and asking the more fundamental question of why do smaller upland rivers respond more rapidly and intensively to climate change compared to the larger downstream rivers?
Oh, thank you for this question. I think I will go back to this slide. Yes, and yes, here we also do a comparative study to look at the response of the fluvial sediment yield to climate change for the smaller upland basin and also the larger basin. So we found that for the smaller basin, their sensitivity to changes in temperature is larger because our reasons there are a few reasons. The first is that for the smaller basin, the coverage of the glaciers and the ice-rich permafrost is larger as compared to the larger downstream basin. So which means that in the upland basin and it is relatively small, and there are more glaciers. So because of the existence of the ice, they are more sensitive to climate change. And also, it is related to the connectivity. For example, for the more upland basins, the longitudinal connectivity, if we look at the riverbed profile from the headwater mountain to the basin outlet, they are more steep as compared to the larger basin. And also, in the upland basin, the vegetation is not so good. Because in the downstream, when the temperature and the precipitation is relatively higher, so the vegetation for our case, they are the permafrost they are the alpine meadow. But in the very upland basin, there are only alpine steppe. So the vegetation could also be important. So in total, there are a few reasons that jointly contribute to lead to the more sensitive landscapes in the upland smaller basins as compared to the larger downstream basins.
Thank you from me, and also thank you from Daisy. So people don't hesitate to write more of your questions in the chat. I'm sure that a few of you are typing right now. I may have a question for you before Rebecca reads the next question, which would be most of the system that you've described as this reaction to the ongoing acceleration of the melt and the increased fluxes that we see from it. By looking at areas where glaciers have already completely disappeared, what can we say about the relaxation time after the melt event, and how long does it take for a post-permafrost, for example, landscape to go back to a steadier system or status?
Thank you, Luca, for this good question. I think it is a $1 million question, and the short answer is we do not know when the landscape will be stopped or the relaxation time. It's really difficult because so far we have the 6 decades data from the 1950 to the 2010, and we are seeing the substantial increases in both discharge and the sediment load. And the future modeling studies also suggest that they can predict the future change of the glaciers. So after for example, for the glacial landscape, after the complete disappearance of the glaciers, but the landscapes they can be still unstable for a quite a long period because of the time lag response of the geomorphic system to the climate change, right? Or we can also use the periglacial theory proposed by Professor Michael Church to explain this kind of phenomenon. But the exact lag of the time I would say is very difficult to quantify. Yeah. And in our case, in the Himalaya case, I don't think that the landscape can be stabilized within the 21st century. Yeah. From my understanding. Yeah.
Okay, thank you very much. No more chat questions right now, but maybe Rebecca or Aditi, Rebecca has one. Go ahead.
I have one. I was wondering whether the model you had there that was combining this kind of sediment availability and transport capacity, whether that's been exported to another mountain range around the world. For example, I'm thinking whether it's exportable to an arid mountain range where you have different relationship between kind of precipitation and suspended sediment.
I mean, whether the model can be used in other similar glacier-rest or permafrost landscapes in other alpine areas. Yes, I think our model, the idea of our model is to provide this model framework. So in this model framework, we consider not only the transport capacity, which is discharge, but we also include the factor of sediment availability. So here is the empirical function of our model. In the SATM model, we also consider more factors to include the snowmelt processes as well as the vegetation effect. So the idea is to produce a universal model that can be used to simulate the SSC in the cryosphere feed rivers. But the rivers could be different. Some rivers, it can be a naval basin that is dominated by the snowmelt processes. Other basin could be glacial basin. For example, the glacial coverage is over 50%. It is a glacial basin, and the glacial processes dominate the sediment transport. And in other basins, they could be a permafrost basin or a fluvial basin that the rainstorms are still important. So we provide such a framework that that you can calibrate your model with. So in each different kind of landscapes, the process could be different, but our model include all these kind of processes. So if this process is not important, you can switch off this parameter and to consider the other factors. But the point is that we need the insight to observe the data to calibrate the model. It could be different. I mean the parameters or for example for the A and B factor in this equation, they can be different, but the model framework could be universal. Yeah.
Brilliant. Thank you.
Thank you for your question. Yeah.
Okay, so we're still waiting for questions in the chat, but I have a quick question, and I think you may have answered that in your presentation, but maybe I missed it. But where you were talking about future projections for sediment fluxes in different areas, so it was the Tian Shan region and then the Himalayas for the glaciers, and the sediment fluxes of like temperature and precipitation effects for future projections. Yeah. For 2050. So do you see that in your future projections and from your observations, which region would you say is more sensitive, like the Tian Shan area, the Himalayas, or more west, I mean, more east towards the Tibetan Plateau, where you have the other sides?
Oh, thank you for your question. Yeah, Aditi. It's really a good question because for the historical data over the past 6 decades, we found that in the western part of the region or the Western Himalaya, or no, we cannot say what Western high mountain Asia, right? Including that mostly they are such river basins, they are influenced by the westerly, and for such river systems, we see the more drastic signal in terms of the increase for the suspended sediment load, mainly because of the larger fraction of the glaciers here. And for the sensitivity, we also estimate, our results also show that for a river basin with higher, with larger fraction of glaciers, they are more sensitive to temperature, but their sensitivity to precipitation will be low. So if you look at this figure, the figure C and figure D, so if you look at the sediment sensitivity to temperature, it will increase with the glacial coverage. But if you look at the sediment load sensitivity to precipitation, it will decrease with the glacial coverage. So which means for a river basin with low glacial cover, it is more likely a pluvial basin, right? It is more sensitive to the precipitation change or the rainfall-driven hill slope processes. But for a river basin with more glacial cover, the thermal processes could be more important, like the temperature drive the glacial dynamics. They can further affect the sediment transport in through the subglacial drainage networks, but also through other thermal related processes. Yeah. So in different kind of basins with different underlying landscapes for different cover of glaciers, that their response to climate change could be different. Yeah.
Thank you. Well, that was really interesting. Do we have any more questions? Okay, so I think even in the chat, there are no more questions, and we are very close to an hour. We actually did make it in time. It's an hour already. So I think it's time to close the session. So thank you, Dongfeng, for a really wonderful talk. It was really nice to have you with us. And thank you to everyone in the audience for attending this talk. And we will see you all next Thursday for another Landscape Live seminar. So thank you, everyone.
Thank you so much again. Yeah.
Thank you, Dongfeng. It was a really great overview of all that research.